critical temperature is the fundamental quantity of a superconductor. And the second fundamental quantity of a superconductor is the critical magnetic field. And both can be measured in the experiment, as shown. And it is clear that every fundamental theory of superconductivity must have in it a formula, an equation for both of these quantities, as shown for two theories, where one of these theories is an established theory which stands in every superconductivity textbook of the last 50 years. And the other one is my new theory. My new theory which stands in no textbook. And what I will do now is the following. I will show you how both of these formulas, equations, are derived. And then I will compare both theories with the experiment, without saying which is which. So now you, the viewer, get the opportunity to compare both theories objectively and choose the one you prefer. And by that choose, if you should think about rewriting the textbooks of the last 50 years. And after that, of course, I say which theory is which, and I say some words about the situation. Okay, first there is the BCS theory, a well-known, prize-winning theory of physics, which was found in the year 1957 and which is the theory of superconductivity. The theory of superconductivity of the last 100 years. Since the discovery of superconductivity in the year 1911 by Dutch physicist Kamerlingh Onnes. And then there is my new theory. My new theory, on which I hit upon in the years 2008-2009 while working on my diploma thesis on high temperature superconductivity, which is a part of superconductivity which is still not understood until today. Also not with the BCS theory. And now I will show how the formulas for the critical magnetic fields are derived for both theories. And I start with the BCS theory, where the thoughts behind each of the steps now can be found in the BCS paper, or can be found in superconductivity textbooks, of course. And the thoughts behind my steps can be found in my paper. Of course, I must say my paper is quite detailed and has quite a length, which is why the thoughts are most probably not so easy to find. But despite of that, I can assure you that they are there. I can assure you that I'm not just putting some couple equations in each other, without thoughts. Okay, and now here we go. So, and now here are the two formulas. The two formulas for both theories. For the two fundamental quantities of every superconductor. The critical temperature and the critical magnetic field. And now to physics. To compare the theory with the experiment. And the obvious experiment for superconductivity are the normal metals. Because for them all the values for the quantities needed here are available from the experiment, as shown. And, which is also not that unimportant, and which is unfortunately not always the case, these values are established, and they are the same in all textbooks. And in the periodic table, these 9 metals are also close together, as shown. These 9 well-known metals. Well-known in physics, of course, as we know well their physical properties, as the ones just listed, for example. But partly also very well known in everyday life. As for example, among them are metals like aluminium, tin or lead, which most of you viewers probably know well. Okay, or probably you know them well, at least somewhat. And, which also fits well, among these metals is also mercury, the material with which superconductivity all started, which was in the year 1911, as said. So, these 9 normal metals are really the obvious choice to test a superconductor theory, to compare a superconductor theory with the experiment. I think it is hard to disagree with that. But the thing is, despite of all this, what I said now about how to make a good obvious test for a new superconductor theory, it all is completely new. We have now over 100 years of research in superconductivity, in which surely 10,000s of papers were produced. So much paper and papers produced and published. And today surely more than ever. And also most of these papers are so specific and so complicated that it is hard to understand anything of them, that it is hard to get anything from them. But then, on the other hand, such a fundamental thing as how to make a good obvious test for the newfound superconductor theory, it is completely new. I don't know, I don't know. But okay, it is what this is, and of course this is also not the topic of this video. But I also couldn't say nothing about it. But okay, now it is set and we can continue with the video. And we can now put the values into the formulas and compute the critical magnetic fields for both theories. And now is your turn, dear viewer, to do some physics. And for that I show you now both theories and the experiment. And you can make yourself your own picture of physics, of which theory fits the experiment better. Okay, and now which theory is which? Which color is which theory? Okay, so it is. And now the question, which theory fits the experiment better? And for that I first show again the superconductors with the low critical temperatures, zoomed in here. For them, as can be seen, both theories fit the experiment okay, acceptably well. But of course it could be better. And also better that the theories could follow better and fit better the characteristics of these 4 experimental points. But still, and of course in the end, the BCS theory fits the experiment here somewhat better than my theory. But then again, on the other hand, and zoomed out again, for the higher critical temperatures my theory fits the experiment better. And also fits it better than the BCS theory fitted better my theory for the low temperatures. And as also can be seen, the agreement between the theories and the experiment is also okay here, as it is in general okay for all critical temperatures. But still, if one looks at all of these points in total and overall, the agreement with the experiment is better for my theory than it is for the BCS theory. And this also again because my theory follows better the characteristics of all these experimental points. Yeah, I think it is okay to say all this like this. And what does this now mean? Well, I think that. Well, I'm quite sure that the situation is the same as the one it would be in heavyweight boxing. Yes, as in boxing. And I mean by that, if one wants to beat the reigning champion, or here now in physics and superconductivity, if one wants to beat the reigning theory, the BCS theory, one has to be clearly better than it. Being just equally good or just somewhat better is not good enough. Or of course, knock it out. And that's what I've done here. I knocked the BCS theory out. The thing is, the agreement between the theories and the experiment lies for all these points between 7 and 52%. Where my theory is here also better, as said and can be seen. But to say clearly better, to say that we would need to take a closer look on all these points, on their exact percentages, how they agree with the experiment. But as said, we don't have to do that because of the knockout. The 2 knockout punches actually, here and here, for mercury and lead, which agree with the experiment with 2% and 1%. And these are really good values, yeah. Also in general, for any theory in physics, to have this kind of agreement with the experiment. Yeah, good physics. Okay, and this is why I now finally, and as a conclusion, say that my theory fits the experiment here clearly better than the BCS theory. Okay, and what does this now mean? Again, for that I show again everything I showed so far. Okay, first we must know that how important is this formula equation for a theory of superconductivity. Okay, we know that the fundamental quantity of a superconductor is its critical temperature, as illustrated here for mercury, with the experimental curve with it all started. And now I see it should be electrical resistance instead of electrical resistivity, because the unit is ohm. But okay, the question is the same if we look at the absolute value resistance or the relative value resistivity. What happens here? What happens with the resistance, with the resistivity at the critical temperature? Why does it drop to 0? And by why I don't mean big talks and pages of text, but a mathematical formula equation with which the critical temperatures can be computed. And are computed. Yeah, are computed. The thing is, here's the formula for the critical temperature of the BCS theory, with its quantities. But nowhere, And you can search for yourself every superconductivity textbook and the whole internet for superconductivity. Nowhere the critical temperatures are actually computed with it. Like here for mercury and the other normal metals. All the quantities on the right hand side of the formula should be well known. And it should be easy to compute the critical temperatures with them, with the corresponding values for all these quantities. But this is done nowhere. Nowhere is computed why superconductivity happens where it happens. Yeah, Okay, this was again off the topic, sorry for that, but I just had to say it again. Okay, the fundamental quantity of a superconductor is its critical temperature. And after that, and also besides that, there's the behavior of a superconductor in a magnetic field, which is also an important part of superconductivity, and which is characterized by the critical magnetic field. And basically it is the same here also. Below the critical magnetic field there is superconductivity and above it not. With the difference that usually we have room temperature which is much higher than the critical temperature. And we have the Earth magnetic field which is much lower than the critical magnetic field. So to get superconductivity we must lower the temperature, and to destroy it again we must increase the magnetic field. Okay, so much from here, and now to here, to the Wikipedia page, because here it also can be seen what I just said. Because this is a typical page for the experimental properties of superconductors in a textbook. And okay, strictly speaking, Wikipedia is no textbook, but it is an encyclopedia, and also a modern digital form of it. But still in this case there are no difference between them, which means this is a typical page for the experimental properties of superconductors in general. If the textbook one is looking at and in even has in it experimental properties, of course, even has in it concrete values from the experiment, which is also not always the case, and which is also again a topic for itself. But if it does have them in it, it usually and firstly has in it critical temperatures of certain superconductors, or transition temperatures as they are called here. And if it does have much extensive experimental properties in it, it usually additionally also has in it values for the critical magnetic fields, as it is shown here, for this typical example page. So, with all this said, it is now obvious to say that, or at least it is hard to argue against that, the two fundamental quantities of a superconductor are the critical temperature and the critical magnetic field. And by that a formula equation for both these quantities, which says, okay, if we have a certain superconductor with certain properties, if it has such a critical temperature, it should have such a critical magnetic field, and the other way around, that this is important for a theory of superconductivity. Or I say, one can even go so far to say that every theory of superconductivity, which claims of itself being a true theory of superconductivity, must have in it such a formula equation. And also a good, presentable one of it. Yes, so important it is. Okay, and second, for that I show again the periodic table. Okay, so of course very many superconductors were found over the last 100 years, where the elemental ones of them are shown here in the periodic table and colored in blue. But of course also, and in addition, there are the many superconductors which are built out of these elements, the compound superconductors. High temperature superconductivity, for example, was found in such a compound. The compound built out of lanthanum, barium, copper and oxygen actually. And then also in addition, there are the superconductors which become superconductors, but only under certain conditions. For example, it has been shown that squeezing a material together, or scientifically said, applying pressure on a material, is something that can become it a superconductor. So many superconductors there are, but I tested and compared both theories for only 9 of them, the 9 normal metals. The thing is, of course one can only test a theory, one can only compare a theory with the experiment if one has an experiment, if one has the needed values from the experiment. And here's the problem. To find values for the critical temperatures is still somewhat possible, but to find values for the critical magnetic fields is already considerably more difficult. And the same or worse for the Fermi velocities of the electrons. Here also it is considerably more difficult to find concrete values for them. And this is a problem in general, the experiment. Because although the textbooks are full of theories, models, equations, mathematics, there's only very little from the experiment. Very little. And this makes it of course hard to compare theory with the experiment. Makes it hard to do physics in general. Okay, that's the situation. And now to superconductivity. To superconductivity where we need superconductors. And at least some group of superconductors for which a theory can be tested. But as said, there's not so much to choose from. And I mean by that a group of superconductors, a group of solids, which are so well understood, which needed properties, the critical temperature, the critical magnetic field, the Fermi velocity of the electrons, are so well known that we have well established experimental values for all of them. And this is maybe also surprising to you, for me it surely was really something to ask for. Not only to have some values from some superconductors from somewhere, but to really have well established values for a whole group of superconductors. That if for this is asked, that there's not so much to choose from. And in my eyes, as I see it, we don't even have much of a choice. Because these 9 normal metals here are really the only group of superconductors for which all this is actually fulfilled. And fulfilled, of course, all this should be. But and of course, because these normal metals are so well understood and well known, on the other hand, they are of course also a good test for a theory of superconductivity. Or are a good test for any theory in solid-state physics. Actually, of course, also. Yes, if a theory in solid-state physics fits the experiment well for the normal metals, then this surely means something for the tested theory. Or at least this is something which is not so bad for the tested theory. Yes, this it really surely is not so bad to have found a theory which, for the normal metals, fits the experiment well. Okay, that was second, and shortly again I illustrate it again. Okay, of course, another obvious choice for a group of superconductors to test a theory are the transition metals, here. But for them we already have the mentioned problem. Take hafnium for example, here. And now let's go to the Wikipedia page, where hafnium is here. But as can be seen, or as not can be seen, there's no value for the critical magnetic field. And this is what I mean. And for the Fermi velocities it is even more difficult to find values for them, for the transition metals. And this is how it is for any group of superconductors, which are a little bit more special, which are a little bit more complicated. Then it becomes quickly very challenging to get the needed values from the experiment. So now we have it all the situation, which is so that I have a new idea to explain superconductivity, all superconductivity, in which I did put on paper this my new theory of superconductivity. And now to give you an impression of this new theory, to help you with the question I think must come up to one's mind here at some point or the other. The question which is, what should I make of all this? Rewriting the textbooks of the last 50 years. And of course, here's some random guy on YouTube, me, trying to tell you that he has solved a 100 years mystery in physics, superconductivity, which by the way, already 100 years ago, physicists like Albert Einstein, Niels Bohr and Werner Heisenberg tried to solve. And now here, 100 years later, and on YouTube, as said, this some random guy tells you that he has solved it, this big physics mystery. Yes, there surely can up the question, what should I make of all this? And for that, to give you an impression, to give you some answer to this question, I've done now this what you just saw. I took one result of this my new theory and also an important result for it, and also important for any theory of superconductivity as said and shown, the formula for the critical magnetic field. And compared it with the experiment with the normal metals, which as also said and shown, are a good test for a theory of superconductivity. And compared here it also with the well-established BCS theory, this well-established theory of low temperature superconductivity. And doing this, it turned out that, for this important result, and for this good theory test, that my theory fits the experiment here clearly better than the BCS theory. Yes, clearly better. And because of this, I now give the answer of and to this video. The answer to the question I asked at the beginning of this video, and the answer to the question in the title of this video. And this answer is... yes, we should think about rewriting the textbooks of the last 50 years. Yes, with this kind of result in the back, I give this answer. This my take on the situation, which is the one here written in red. Yes, we should think about rewriting the textbooks of the last 50 years. Okay, that was the big answer of this video, but I now still say some words, some sentences about all this. Okay, maybe first. The thing is, in this world, in our world, it is often only right or wrong, black or white, or if you are not with me, you are against me. But often also the world isn't like this, and here it truly isn't like this, because the BCS theory and I, we both are on the same side. We both try to explain superconductivity. But of course, since after all explaining superconductivity or in general doing physics is comparing a theory with the experiment, I've done now here also exactly this. I compared both theories with each other and with the experiment. Man against man, so to say. Okay, so to say it's just theory against theory in the end, of course. But as said, this is now against each other in the sense of in this direction or in the 180 degrees opposite direction. And actually, I think the both directions we both theory go are actually quite very close to each other. And here I come to another point I still wanted to say. Yes, I think as I see it, the both theories go practically quasi in the same direction. But my theory goes further. Yes, this is how I see it, that my theory goes further, deeper along that path, goes deeper in this direction. And maybe even goes all to the end of this path of superconductivity, of explaining and understanding superconductivity. So far this is even possible for any theory to go all to the end, explaining and understanding something completely, and whatever this again of course means. And I know these are big words, but, well, let me just show you it quickly. What I think could be at the end of the path of superconductivity. Its fundament, hence so. And again I show it with the experimental curve where it all started. Okay, the question is what happens with the electrical resistance here at the critical temperature, or exactly here at this point, what happens here? And I say my answer is something new physics happens here. The charge carriers in the solid come to a point here which is a border between our known classical quantum mechanical world and a new world of new physics. And this border here, below which there is this new world, I say now is given by Heisenberg's uncertainty relation for energy and time. And this is my idea now, yes, my fundament of superconductivity, to now take Heisenberg's uncertainty relation for energy and time and insert it into the Drude formula. The Drude formula, the fundamental microscopic formula for the electrical resistivity, for the electrical resistance, which can be done since temperature is energy, and is also energy of the charge carriers in the solid, and which this energy is given here, and determined by the Boltzmann constant Kb. So, and now of course all these equations formulas can be inserted into each other, and can be equated. And from this of course values can be computed. Needed values for needed quantities can be computed. And superconductivity could be explained with them. And from this fundament here, out of it, hence so. Okay, that was that. But what I actually really wanted to say is that, okay, as said, I think the BCS theory and my theory go quasi in the same direction, are very close to each other. But how close? Well, about that I don't know. But I actually think about that to know is also actually not that important. Important is just to know that they are close to each other, which they surely are. And okay, now I come to, finally, the point I still wanted to say, which is, okay, of course the BCS theory helped me, inspired me. Yes, of course, it makes everything much easier if one knows in which direction to go, roughly at least. Yes, easier, helped and inspired, the BCS theory surely has me to find this new theory. Yes, surely has, 100%. Okay, and maybe still, in this context, I still say another thing. Okay, of course, because of all this, the theories being so close to each other, one can maybe get the impression that my theory is nothing new. It's just a copy of the BCS theory. It's just the BCS theory in other words, so to say. But okay, if one really looks at my results, my thoughts, it should be obvious that this is not how it is. Yes, for example, the formula for the critical magnetic field of my theory is different, substantially different of that from the BCS theory. And yes, the idea with equating Heisenberg's uncertainty relation and the Drude formula. Well, this idea is so far away from all known theories of superconductivity there are, so yes, it is really surely new. Yes, surely. Okay, and that was that, also now said. And I now come to my final point I still wanted to say about all this. The thing is, in my big answer of this video, written in red in the red box, as you probably remember, I used the expression think about and used it with intention. Because here also it is not just black and white. Yes, I don't say and mean, and I can promise you that from now on, my theory of superconductivity should be the new theory of superconductivity. And all other theories of superconductivity should be, also from now on, should be no longer be considered at all. Yes, that I don't mean. And by the way, this wouldn't even be possible, because my theory is not a closed, finished up theory. And actually it is quite far away from that. It is more the opposite of that. It opens up something new, a new field of physics, as I already said earlier, with the blue circle in the electrical resistance curve for Mercury. And my theory, my paper specifically, is just my part to it, what I have to give to it. Yes, that. Okay, and now to my final point, which is, and I finish these about all this words, sentences, how I started them, with, in this world, in our world, there are situations where we have something for a long time, like here the BCS theory for the last 50 years. And in this time, this something establishes itself, like here the BCS theory. It is in every superconductivity textbook, or in general, it is almost everywhere where superconductivity is. And big prizes it, the BCS theory has also received, and deservedly. So, and in these situations it can happen. And I don't know, but maybe even this happens almost always. It can happen that this something becomes something which it is not. It becomes established for a long time. This something, it becomes untouchable. It becomes flawless. It becomes something which is not questioned at all, about which it is not thought about at all. If it is really the end of the path. If there really isn't something better. Or to say it in short, it becomes something completely white. And this it is not. Or okay, if there's not such some things in the world completely white. But here in physics, I think it is okay to say no theories, that absolute and unquestionable. And this is why I use the expression think about. Because this is the situation we have now, in my eyes. Think about. Yes, think about superconductivity and its theories. Question it, them, and the situation we have, how it really is. Always provided, of course, you can relate to what I here spoke out and showed out. Provided that, of course. Else not naturally. Else no think about that. Naturally, of course. So that was the physics part of this video, but because, okay, of course, actually I don't know, but because I think there is the possibility it could be that I worked out this video good enough to get your attention during it and for its contents. Yes, because of this and because of, I think it could now also interest you. I give you now quickly my situation. Say quickly something about my person. Okay, as said, in the years 2008-2009, I made my diploma thesis on high temperature superconductivity. And in this time I had this idea that I showed here. And actually, if I remember correctly, I even had this idea quite early, a couple of months after I started it, the thesis. And the situation was, first I tried to understand superconductivity with the existing theories, foremost with the BCS theory of course, but I just didn't get any access to them and the BCS theory. Okay, of course I could and still can relate to and comprehend the mathematics in the theories, how the equations are put up and how they are then solved step by step. Yes, that okay. But what I mean is really understand something, really get access to it, to superconductivity, that I never had, that feeling to have I never had, and not even close. And this is why, from some point on, as I realized I wasn't gonna get that from the existing theories, I tried to understand superconductivity on my own. With my own understanding of physics, thus. And so then, by doing so, I came then up with this you now also have some impression of. Where to my final work, I published on my website, to which the link is in the description, where to my final work, it took to the year 2015. Yeah, then I finally published it. My work, my theory, on my website. And the reason is, essentially the reason is, no one I showed this, my new thought, my new results, reacted to it. Yes, that it is, really basically. And okay, of course, there were some little reactions, or more very little reactions, and these reactions were also only about outer things like a typical reaction was that the argument that we already have so many theories to superconductivity and we understand it so well, we don't need nothing new. But no reaction to the physics, the idea, the result. Yes, that not. Here truly no reaction. And okay, in the beginning at the university, during my diploma thesis time, I was of course insecure. And this in general, yes. And on top of that, also of course, this is the time one is for the first time in contact with the real physics world, which is surely different from the idealized picture, how it is presented to one to be, up to then, until then. Yes, there was that, but actually despite of that, the main thing still was, I think, as said that, our understanding of physics, that of my supervisors and mine, that they were so different that, yes, they were just different. Our understanding of physics. Let's leave it to that. And because of this, I then stayed focused on the diploma thesis and finished it in 2009. And after that, after I finished it and left university, because because I just had the feeling I had to now leave university and universities in general and dedicate to this my idea some time and doing that on my own. And this is what I then also did and worked out this idea, this thought I had during my diploma thesis time into this work here and available on the website. And did this thus, working out this work in my private time as a private person. And now to the reactions. Well, I'm not gonna go into large extensive details here. And I also think this is also not really necessary, just how it overall went. In the first years, until the end of 2011, I wrote everything I had to it to the idea on paper and tried to publish it on one of the big famous American and British journals of physics, whose then purpose it is to publish new research results in physics, but got always rejected immediately, without any comments. And with that, or after that experience, I then somehow left it alone. My theory and my new results. Until the year 2015. Then, after the advice of my father actually, to still just put the work out somehow, as it can be done on an own website, I listened to him and did that then. And before that I had cutted the work down to its now final and present form, that which is available on the website. But this was just for outer reasons, this cutting. The inner content, the substance, the results, I did not touch in this. And then, again, I tried to publish it on a big famous journal of physics, this time an European one. And here it was where I received some of the nothing new is needed reactions mentioned earlier. Or of course, in the end, bottom line, this means of course that my paper, my theory, got rejected by the journal to be published by it and on it, due to this reason, due to that nothing new reason. And after this also didn't work, I still tried one thing. I wrote and did send out 200 to 300 letters, short letters, which basically said also shortly how it is. My situation, my idea, and for the impression of it, I also already back then, added to them also my formula for the critical magnetic field, with its derivation and how it fits the experiment. But no reaction. And of course I must say my intention with these letters was also not to get a reaction or to get some kind of appreciation or pat on the back or I don't know what. I just wanted to show it. Just show that somewhere out there this exists. This my other and new view on physics and superconductivity. Just wanted that they know it. That there is such a new view with such new results out there. Yes, that. Oh, and by they I mean physicists of the older established generation of physicists, to whom I did send the letters. Physicists which were in leading positions in leading universities, or of course universities which were, and probably still are, considered to be leading worldwide. Yes, to them physicists, professors, thus mostly, I did send the letters, but as said, no reaction, or as good as no, practically, effectively, no reaction. And after that then, I again, or thus once again, left it alone, it my idea and theory, or in general left, once again, the physics in my life, the physics part of my life alone. Yes, this is probably a good way to put it. Until the year 2019, and until now, until today. So thus after over 10 years now, I'm still, or again, on it. Still again, the idea of physics, it is again a part of my life. But why? Honestly, because I still can't make sense of all this. And of course, because still, this year I found the whole approach and its results, they still feel so new. Yes, they still feel so new as if I would have found them. Yes, maybe even as if I would have found them like about 10 days ago. But not 10 years. Yes, like that it surely doesn't feel. Like something which is now over and about 10 years old. Surely not. And this is probably also why I still have the energy to do all this. Or to do all this once again. But okay, back to the making no sense of all this. The thing is, on the one hand, from the outside, of the outside physics world, of the established leading physicist, I received back as good as nothing to my new physics research results. But then again, on the other hand, from the inside, yes, from the inside of me, I surely got something back. Yes, from these new physics research results and findings. And this is yes, about this I can't make sense, because I know the results are there of the theory, and that they are also good enough to be confronted with them, as showed for the one here just presented. But that they are so overlooked, or disregarded, or whatever the right appropriate word it is for it, that I don't understand. And still, after all, the results are still the substance of a theory. Or do I see here something completely wrong? Have I lost here reality completely? And all other, everything around them, around the results, how they are derived, the mathematics, the thoughts behind them, and of course, the big talks and big texts around them, around the results, yes, they are. Yes, in the end, they stand and fall with the results. Without the results, all this other, around stuff becomes meaningless, becomes of no substance. Without results that fit the experiment well. Okay, and this is why I created this YouTube channel here in 2019, when I did put and publish my first video on it. And this video is now my second one, my second video on the channel. And I came up with YouTube. I chose YouTube because one, the how I can present the theory here. I can go in depth here, as you probably also already have noticed, about physics and superconductivity, how I see it, how it is, what its heart, its substance is. And this, of course, I could not do, at least not in much depth, in the paper. Because here, of course, for scientific papers, there are, of course, guidelines, or rules maybe even, after which they must be written, in which they must follow, so that they are all in the same form. Yes, like for example, how I had to here deeply emphasize and point out and also defend that a formula which relates the two fundamental quantities of a superconductor with each other, that this is important for a theory of a superconductor. Yes, for such a thing, such a fundamental taken for granted thing, which but is completely new. Yes, for such a thing, I believe one needs something other, because in a standardized scientific paper there would be no room for that. I believe that. Okay, so far the depth, but also of course there's the appearance, how I can present the theory here. Because of course what comes with the standardized paper form is that this form is boring. Everything has to be written down to what one has found. Every thought, every equation. And as said in the standardized monotonous form, in which nothing is highlighted, emphasized, or especially pointed out. And this leads of course to that also the most impressive, best thoughts equations found become only some of many. Some of the many thoughts equations which build up the paper and which determines its form. And which is, that's what it is. But here on YouTube, not only here of course, but surely also here, this is different. The opportunity to present what one has found, openly and freely as one, or here as I, wanted to present it. Physics theory. Yes, here YouTube truly gives one some opportunity. Openly and freely present what one has found. Where another story is, of course, how I succeeded with this, the presentation, the appearance. But anyway, the opportunity is there to present, definitely. And with that also, there are no excuses now to make. Okay, that was one, the how. And now to two, the who. To who I can present the theory here, which is practically, effectively everybody. Everybody with internet access. And this of course also is different from so far, where I presented my idea only to a very narrow, very specific group of people, as said. And now here to everybody. Here I can reach practically, effectively everybody. And now to you I reach about 3, why I did do this video. Again, honestly, because I still want to show it, same as the letters does. Show it, what I have showed here. Yes, that it is, honestly and really basically, and not more. About more I have not thought. I have no further big plans or further big expectations or intentions behind this. I just still want to show it as said. And what? Or if there is a what at all, of course, what happens from now on? Because I said in my eyes, from my understanding of physics, this is something I found. Something worthy to be looked at and something worthy to be confronted with, to physicists. And now if I think of it, probably also not only physicists. Because the fundamental point, the fundamental scientific question here, yes, here is so fundamental. Yes, here is so fundamental that it is easy to understand, also in general. And to leave the work just on my website, I think that would have not been enough to show it. Or to just keep leaving it on my hard disk or on my shelf, above my drawer, with my underpants actually, the work, printed out and catching more and more dust, I kind of somehow think would have also not been enough to show it or for someone to hit upon it. So, and with that now, that's it now. Not so much about my person, I know, but about my situation. That yes, that certainly and quickly. And about the video, of course, why it exists and why you are watching it now. Now and apparently seemingly still. Okay, and one last thing I have. And that one last thing I have to you. To you, the older established generation of physicists. Yes, to you. And it is about, if it happens that, yes, there's this big if of course. But yes, if it happens that my idea and results come to you, find a way to you. Yes, if this happens and you decide to take a look at them, at my new results and idea, you, the older established generation of physicists, you decide to take a look at them? confront yourself with them, and deal with them. And doing all this truly and seriously. Yes, if this happens, then, and I know this sounds hard what I now say, but I have to say it, then there's one thing I don't want to hear from you. Yes, and I really don't want to hear none of that thing, really and seriously. I can promise you that. Yes, I'm tired of this thing, this one thing, and I really don't have energy for it. And it is a thing I myself experienced some of it, and it is a thing I see also others experiencing. And also not only in physics, in the physics world, but everywhere, all over the world actually. Others experiencing of that thing also. And also of course experiencing much more of it than I did. And which is the following thing, the following reaction of you to someone who has found something new. Or of you to someone who has found and has now a new different opinion. Different from the opinion which is seen so far to be the right, absolute, unquestionable one. Yes, I don't want to hear any of that kind of argumentation, that kind of discussion. And I will not have it either, any of that. I simply have no energy for it. But if you do have the energy for it, okay. And if you want to argument and discuss in this way, then also okay. But then just not with me. Then there is just not that kind of argumentation or discussion with me. And then, if you still nevertheless want to do this with me, then it is the best you just choose again the reaction, no reaction. Yes, then just choose again the reaction, no reaction, towards me. I prefer that then, and prefer it gladly. But okay, enough said, and now to the one thing I talked so much about here, which is the following thing. I'm a big famous professor from a big famous university, and you are a nobody from nowhere. So it is clear it must be clear that your idea can't be any good. Yes, as if to say, if I, the big famous professor, who has worked his entire life, whole decades, in and on physics, and in and on leading physics. Yes, if I haven't come up with such something, with such an approach in my life, and on top of that also such an easy and obvious approach, yes, then it must be clear that it is completely excluded that such a fundamental and new approach even exists. Yes, completely excluded it is this. And the end of the path it is also with that argument. End of the path and case closed. Oh, and by the way, just as a short comment from me, easy and obvious, the approach is of course also only in hindsight. Okay, there are and were published so many works in physics, or papers they are called them, the published works. Yes, so many works, papers there are and were published, worldwide and globally. In journals of physics of course, but of course also in these days, there are of course also the new modern digital online archives, on which one can put and publish one's work of physics. Yes, so many opportunities there are to publish, and published there is also a lot of, in physics, and probably also in other sciences as well, it is the same. But anyway, the point is, so much is published in physics over the years, so lots of papers which are all full of and filled with new, meaningful, significant, crucial physics. Yes, else they would have not been published. Yes, they are of course all published because the physics world sees in them the absolute necessity to be published. In all of them, there are much and lots of papers, but among which your work, your paper, is not. And this is the point. If your work isn't even that published, if the physics world doesn't even see the necessity to publish your work, then it can't be any good. it is as that, then your work simply can't be any good. And just to illustrate it again, we are talking here about 10,000s, 100,000s and more of papers published over the years. And every year it is getting more and more. And also more and more, not only every year of course, but every year per year. The number of published papers per year becomes more and more. So thus, these days, it is as easy as it has ever been to publish, because it is as much published as it has ever been these days. And you must remember and consider that all these published papers, the 10,000s and more, that they all were severely reviewed and examined, so that they then also are all that new, meaningful, significant and crucial, which are the requirements and the standards every scientific paper must fulfill, so that it can be, and then of course also is, published. And of course also it must be one's own work. Okay, that should be self-evident. Do not copy someone else's findings and results. But yes, through these requirements and standards, it is made sure that it is guaranteed that every scientific paper is that. And of course in reverse, it is then also made sure that, guaranteed that your work is that not, cannot be that, impossible to be that, new, meaningful, significant and crucial to physics, if it isn't published. It is as simple as that, and as guaranteed as that, and as sure as that, period, point, and the end of it. And here also a short comment from me. Of course, in a perfect world, this all would be true, but I don't believe we have that. I believe the real world, the reality is different from that. And I also don't say this lightly. I have something behind it. Like here, one can of course put all kinds of requirements and standards out there, which every published paper must fulfill. But decisive is of course how these requirements, standards are put into practice, how they are put into reality. In here I believe these things, one's new findings being that, new, meaningful, significant and so on, play only a minor role. Much more important are here outer things like the status and position one has, the affiliation one has, the relation one has to the person who reviews and examines your work, your paper, and so on. I believe that, and I don't believe that lightly, as said. But okay, yes, none of all that, only simply physics, with me, towards me, only simply physics. And in terms of physics, I still also have something to my new formula. If you say my new formula, or in general a formula which relates the two fundamental quantities of a superconductor with each other, the critical temperature and the critical magnetic field. Yes, if you say this formula is not important for a theory of a superconductor, and by that of course also everything I here spoke out and showed out is also not important, then this is okay of course, then this is your opinion and how you see it, no problem. But if you say that, if you make that argument, then also justify and explain it, why this is so, why this formula is not significant and not important for superconductivity. And of course I here compared both theories only for 9 superconductors, the 9 normal metals, with the experiment. And thus of course you can say that, you can make the argument that these 9 superconductors represent only a small fraction of all superconductors there are, so, which is true of course. And if this is your argument, your statement and opinion, then this is okay of course also, surely okay. But, yes, but is here of course also. But yes, if you say that, then you of course also at the same time say that these 9 normal metals are not important. Yes, you say by that, of course, then also that these 9 normal metals are not good representative superconductors. And by that, of course, also that a test with them is not meaningful. Yes, this is what you then essentially say. that these 9 normal metals are not a good meaningful test for a theory of superconductivity. And this of course then also justify it, explain it, why you say that, if you say that, and back it up. And back it up with the corresponding concrete values, with the corresponding test and experiment, for which then the BCS theory fits better, for which then the BCS theory fits the experiment better, clearly. As it could be imaginable, well, in a more low temperature region, because of course the BCS theory is also a more low temperature theory of superconductivity, has its strengths here. But okay, anyway, if you say that, make that argument and statement, then back it up also, as said with the corresponding concrete values for all the needed quantities, the critical temperature, the critical magnetic field, and the Fermi velocity, and compute with them the corresponding theoretical values, and compare them then with the experiment, as it is done in substantial physics. Theory and experiment absolutely and clearly, yes. And also of course then also say from where you have them, the experimental values for which the BCS theory fits better. For this then, good and meaningful test. And for this then, good and meaningful, important and representative group fraction of superconductors tested. Okay, I now here also did go somewhat wider, further deep. But I did this here also, of course, because these 2 points here, these 2 questions here are the decisive ones of this video. On them all further is based, and from them all further comes. Now, if it comes from them 2 questions, which are where A, is the formula I here presented important for a theory of superconductivity? And if the answer to this A is yes, then B, how can the formula, be tested? How can it be well and meaningfully be tested? Yes, on these 2 questions everything comes down to what you make of this video. This nobody from nowhere, some random YouTube guy video about his new idea and theory to superconductivity, this big 100 years physics mystery. Yes, what to make of that? And yes, that I asked myself also. Okay, and now here, for the last time, and as the finish to this video, yes, here again, it is again the heart, the substance of this video. The heart, the substance of this video. The critical temperature and the critical magnetic field. The 2 fundamental characteristics, quantities of every superconductor, or at least of every type 1 superconductor. Type 2 superconductors have of course 2 critical magnetic fields, the upper critical magnetic field and the lower critical magnetic field. But where of course in this context it should be said that all these different critical magnetic fields type 1 and type 2 superconductors have, yes, that they all are not really totally independent of each other. All these different critical magnetic fields, they are connected with each other and they are related to each other, so that they are not, as said, really totally independent of each other. All these different critical magnetic fields. But anyway, a short by the way again from me. By the way, new formulas for them. For these 2 type 2 superconductor critical magnetic fields. The upper critical magnetic field and the lower critical magnetic field. I would have also had in my paper, by the way, new formulas for them. But anyway, back to here. Yes, back to the critical temperature and the critical magnetic field. And the experiment. Yes, and the experiment. Yes, and the experiment plotted down here with these 9 black boxes. Yes, here with these 9 black boxes. It is shown, the experiment, graphically plotted down. And where each of these 9 black boxes here stands of course for 1 experimental point of one of the 9 superconductors tested. Yes, 1 box for every experimental point for every of the 9 superconductors tested. 9 points thus in total, in which were of course the 9 normal metals, the 9 superconductors tested. Here, the 9 normal metals which were so close together in the periodic table, as you probably remember, from cadmium to lead, this group of superconductors. Yes, so close together they were there in the periodic table, this group of superconductors. And also not only so close together, but also so peacefully so close together. They were there, this group, these 9 normal metals. Yes, the experiment. Yes, and then there are still also, of course, then yet the theories, the BCS theory and my theory, which are plotted down here with, or shown down here with these balls, with these red balls, these 9 red balls for the BCS theory, and with these green balls, these 9 green balls for my theory. And where each of these balls here, these 9 balls, stands of course for one theoretical point. Yes, one ball, red or green, for each theoretical point, for each of the 9 superconductors tested. Yes, each ball here, every ball here is of course placed where the theories predict them to be, placed at exactly this point, at exactly the point where the theories and the corresponding formulas in them predict them to be, them balls. For them 2 quantities here, the critical temperature and the critical magnetic field, and for them superconductors here tested, the 9 normal metals. Yes, at these points here, at these positions here, the theoretical values are for both theories. The theoretical values of the BCS theory, computed by the BCS theory, predicted by the BCS theory, where the red balls are, and the theoretical values of my theory, computed by my theory, predicted by my theory, where the green balls are. Yes, where they are, their exact positions, predicted, computed by the corresponding formula of the corresponding theory. Where they are, the values, the balls, for each theory, for each of these 2 theories. Okay, and now here it is then again, the heart, the substance of this video. It's physics, it's versus the theory, the theories, and the experiment. Yes, here it is again. So and now here is the question now, of course, why did I do this again? Why did I show you this again? This graphic here, with its points, values, boxes, balls, physics, and results in it. Yes, why that again? Because of what appears here now, and because of what appears here now. Yes, because of these 2 reasons that just appeared here, I did this and I do this here again, this here right now. Because here everything becomes simple and straight and fair. Here at the heart, the substance of physics and of this video. And therefore also the boxing ring with its gloss in it or on it, above it appeared to represent that and as a symbol for that, for acting like that. Straight, fair, plain and simple. Boxing, yes, like that. And heavyweight boxing I chose, this division I chose, because I think it is okay to say that superconductivity is that, a heavyweight problem in physics. Yes, with that history that superconductivity has, I think it is really okay to say that superconductivity is that heavyweight in physics with that history. But back to boxing, for what I chose it to be here, to be in this video, this physics video, to represent that, being acting straight, fair, plain and simple, pure and direct. Yes, for that reason, it is here, they appeared here, the ring and the gloves. And for nothing which is around that, and for nothing which is out of that, outer that, and which is yet to resist outer around that, of being that, of acting like that, is such as to make big talks without proving, and without even trying, without even making the attempt, without even having the intention, the purpose to prove them, the big talks one has made, or to already make in advance. Yes, to already make in advance excuses, weird strange excuses, why one can fight, why one can just do some physics oneself on one's own. Just oneself on one's own, develop one's own theory, with the corresponding one's own then also formulas in it for the experiment. Explain, fit it without excuses. Do one's own physics, do one's own thing. Or which is that also, is hiding behind belts in boxing, which one has attained during one's career, and surely also has deservedly attained them belts in boxing. Deservedly, obviously attained them. But in physics, yes, in physics, the corresponding is to that hiding behind titles, hiding behind positions one has, one holds for oneself, and which one has attained the way one has them attained, them titles and positions and statuses and affiliations during one's career. So, and also not, which is of course also outer around that, of to, hiding behind, is of course the hiding behind published papers. Yes, the hiding behind published papers. Behind the many papers there are and where, and one has of course also oneself published, or correspondingly in boxing, the hiding behind one finds. How many fights there are and where, and one has won. Okay, but in this concern here of hiding behind, yes, in this concern here of hiding behind, belts, titles, positions, one fights, papers, and so on, it should still, or I should still, be said that, of course, this all here, all these past achievements, attainments one has had made in one's career, yes, of course, they may, of course, and in certain particular cases, they surely also are. Yes, they surely also, undoubtedly surely, also are that very impressive, very significant and very meaningful to their areas. But in this context here, they are that not. In this context here, of facing something new, of being confronted with something new, they are that not. Here only the actual moment counts. And all one's past achievements, attainments one has had made are become no longer meaningful, are become no longer significant. That moment that one is confronted with something new. Here a new theory, or here a new opponent. And in general just a new challenge in life. If one is confronted with that new, then only the actual moment counts, and all one's past achievements, attainments one has had made are no longer there for one, help one no longer. That moment are no longer relevant, matter no longer. That moment then. So, and or, which is that also, not that out around is. Yes, is this the kind of small, narrow over? Yes, this the kind of being, of just being too over-precise, too over-correct, too over-picking every single detail there is to overpick from this kind of being, or just even this kind of trying to start to have to lead such a discussion, such an argumentation, is that of course also not. Wanting this, that, of how important something is, In this case here, of how important the formula which relates to two fundamental quantities of a superconductivity such are the critical temperature and the critical magnetic field is, and in this case here also, of how important the 9 superconductors tested here are, the 9 normal matters. Yes, of how important they now are as a test for superconductors. Yes, this is that of course also not. This kind of arguing, discussing of how important if they, the formula and the superconductors tested here now really exactly, precisely now are. If they are a little bit more or a little bit more less, or a little bit more less of a little bit more less of being somewhat more important, or whatever else there still is in between that, or above, below and beyond that, all these different stages of being important, all these different stages, steps, degrees of being important, they are also of importantness. Yes, this is that also not, and also in general not, and it also doesn't lead to much. This kind of being, reacting, and arguing, discussing, you probably also know, are familiar with, recognize it, have experience with, it that doesn't lead to much and doesn't help one much. Getting anywhere where one wants to get to, new findings, results, insights, or where else one wants to get to, wants to look, find, searches for one. At least this is so in my eyes, from my judgment point of how I see it. This kind of arguing, discussing, being, reacting, of how much it leads to and of how much it helps one. This. But okay, apart, independently from all that, one can truly, yes, so far I go here to say one, or even we, can here surely agree, arrive, settle on the fact of matter, that go so far to make the statement, that, yes, that, make the statement, agree, arrive, settle on, that, yes, that. Both these two, physics, objects, items here, things, the formula and the superconductors tested here, yes, that they both, the formula and the superconductors tested here, have their place and have their importantness in superconductivity and for superconductivity. Yes, so far I go to state that. And also to state that here immediately, for all, in all names, saying we, using the word we, here immediately and in general, we all as I go so far that we can here surely agree, arrive, settle, say, state on, that, yes, on, as said, we, The formula which relates the two fundamental characteristic quantities of a superconductor with each other, and the 9 well-known normal metal superconductors from cadmium to lead, that they all have their place and have their importance and their reason to be, to exist here in super, regarding, concerning, being, or starting to be maybe, engaged here in superconductivity. This, yes. Without further over-precising, over-narrowing, over-being too small, close-minded, over-correct of how exactly precisely this now, which is exact degree magnitude they now have of importance, without not going there, not over-picking it there, overly, partly, detailed it. And of course, analogically, as in boxing, some fights and some fighters also just have their place and just have their importance, their reason to be, to exist, rightfully, obviously, deservedly, without further anything, exist in it. But yes, those were the such as I thought of, that came to my mind, at least now here, of being out or around that, why the ring and the gloves appeared here yes, plain simple, straight fair, pure direct, man against man, physicist against physicist, and theory against theory. And thus, therefore, because of this, the reason, theory against theory. This new theory is appeared here. This new theory is also here, appeared also here. Additionally, besides next to, here also. Additionally, besides next to represent that, and as a symbol for that, theory against theory, and the experiment. Theory, experiment, physics. Yes, because of this, the reason, the new theory, is also, appeared also here in addition, as the second and as the other, because of reason why I did this, and why I do this, of course, here again, this here right now. This new theory here, this new, hypothetically, new theory here, still unnamed, of course, it is new, but with a blank, black bottom line here for that, the name, if it is hypothetically found, to then can put the name there, on it, in it, there well, put there well, on it, in it, it can then be well put, new theory. With its 9 light blue, and in each of them inside, as can be seen, spotted 1, 2 question mark in 9 theoretical balls for the new theory. 9 light blue with 9 blue question marks in them, within them theoretical balls. And placed, of course, where the theory predicts them to be placed. At these points, at these positions here, at these theoretical points positions here, where the theory computes them to be placed. And as it is shown here, graphically, plotted down, shown down here, graphically, where they are for this new hypothetical new theory here, which is appeared here also in addition besides next to, because, yes, in additionally besides next to here also, because, yes, because. Yes, because here it is all. No more to say, actually. Here every, me as I, superior physicist, can here show here proof here that he is that, the clearly, obviously, deservedly better superior physicist. To me, all as I, we here, that he is that, the clearly, obviously, deservedly better superior physicist. Absolutely is that, by finding such, by developing such kind of a new theory here, such, with the corresponding, of course, then also in it, formula for this graphic here and its quantities, which then fits the experiment clearly better than my theory in turn again. Yes, by finding such, by developing such a new theory again, which fits the experiment better again, clearly better again. Or for the last time, the boxing analogy. Develop the theory that knocks me out. That just knocks me and my theory out. Nice and clean and clear. Yes, just develop that theory that does that. Knocking me and my theory out. Nice and clean and clear. Obviously, deservedly out. By knockout. Yes, that does that. Just. And by that, of course, also by all that, finding, developing such a new theory that does that. By that, of course, also everything I hear in the last minutes, in this one last thing, in this finish to this video, said and spoke out, being outer around, and being, reacting, arguing, discussing like that I didn't want to hear any of, none of that. Yes, this all, everything of it. You now listen to, gone through now and not repeated now. Is this all? Everything of becomes, is of course instantly irrelevant. Of it all, everything, with such a theory found, yes. Yes, is then simply with such no longer to be needed, to be relevant, becomes irrelevant, becomes unnecessary. Its aim and purpose to prove, to show how better, how superior all this is, makes one. All this listed, listened, gone through now. Needless, irrelevant, unnecessary, to be brought up to, be dig up to, out, all this, that, with such a new theory found, all proven, shown, nothing else needed, necessary to prove, to show anymore. With such, it is sufficient, sufficiently proven, shown, no more is necessary, condition with, such a, of a new theory here, found. Simply all, here, yes, such found. And of course also here also. It is of course here also all in general physics. Displayed, illustrated just here for by of superconductivity. By the specific custom pass piece of it. Graphically shown, plotted down here, displayed. And if one wants to explain, understand, fit it, then this is of course one pass piece of it. Of explaining and understanding it, superconductivity. But this is of course in general also all fitted, theory and experiment, explaining, understanding, doing it, physics. Also all in general, there is the experimental points, values, positions, plotted, shown down here with black boxes, here with these 9 black boxes here. Yes, but in general it is of course open, freely, choosable, selectable, how they are displayed, shown, plotted down. These, the experimental points, values, positions, and of course of how many of them there are, they are, them are, black or whatever, boxes, the experiment. And which one chases, of course, as physicists with a theory, wants to get close to, near with, the ones, them, wants to fit, explain, understand them, near close with them, the ones, the theory. Theory, experiment, physics, or of course the other way around, there is, find, develop a completely new, independent new theory. And then the experiment must explain, show, prove that, if it fits it, the theory, the experiment. The other way around, experiment, theory, physics, explain, fit, understand. And but where, of course, in general, it is, of course, some of both. Some theory and some experiment one has to start to begin from. Some gray one has to start to build from on. Not one or the other, completely zero, black, white. But yes, this is it, then all, to physics here. Of course, here in the specific, particular, one singular time configuration for this specific, particular, one singular part piece of one singular particular part piece again, of, yes, of, and so on, again, the large, grand, big, main, total, whole, or so. But still, of course, as a general illustration, I think it is good of what physics is. Theory, experiment, chasing each other, trying to fit, trying to get close, near to each other. A good general illustration for that. Displayed, it is this here. Yeah. Here. The absolute order to do one's own physics, one's own thing. As already said earlier in one of the first outer rounds. Here it is, one can do that. Trying to understand, fit it, physics, chasing it, them, the boxes, points, values, positions in general, with formulas, equations, putting First, of course, choosing them, electing them. Then formulas, equations, one understands to be the ones right. And then putting, understands these formulas, equations in each other, solve them, and then if they found the formula one has found, then fit the experiment. Yes, this. Yeah. Okay, that was that. It. Then now, I guess, with the video. Now the final bell has rung. Bells. And of course all reasons to still show something, also now disappear. Both these two things, reasons here, now also disappeared, gone. I guess that it is the now. With, most likely, probably with, guess with, the video. Or more than that, of course. Very surely that was that. The sign, the finish, it. At least officially, some unofficially I still have. But officially now, that was that. It finished. The video done and finished. Now yes, with that. And I say no bye to you. Okay, now the video is done and finished. Well, let's say officially done and finished. But still I would like to say one more thing. Unofficially, so to say. One more thing I have on my mind. And I say this directly to the young generation of physicists. My generation of physicists. Well, of course I cannot promise you anything, but about what I am sure is that my theory, my thought, my approach, whatever you wanna call it, has the potential to become something big. And I say this because, well, there are a few things why I say this, but I now give you two of them. One is, if you think of the derivations of both formulas. On the one hand, the BCS theory, a mathematically challenging, very challenging derivation, with quite some length also. And then my derivation, yeah. And this is the one thing, because this is how it is characteristic if you hit on something big. Things which are before complicated and challenging and have great length become short and easy, and fit the experiment also better, of course. And the other thing is, my idea, my thought, looks at something very fundamental in physics, which is the question, where do interactions come from, how they come into being. And this would be, of course, something big in physics, if we could answer this question. And for those who are interested more, here's the idea, quickly told. Well, first we know that temperature is energy. Or more precise, we know that temperature is the measure of excitation energy of particles. And that the excitation energy decreases with decreasing temperature. Okay, so far so good. That we know. And now my idea. I think that if the temperature is lowered at a certain point, particles start experience a limit for their excitation energy. And now, to maintain their excitation energy, particles start having another excitation energy. Here, and in addition, which I call the virtual excitation energy. And this new energy is now used by particles to interact with each other. Here. And this is the idea, quickly told. And I believe this limit is given by Heisenberg's uncertainty relation for energy and time. Because this relation is used often when we reach some kind of quantum mechanical limit. As for example, the limit for the ground state energy at zero temperature, which is also given by Heisenberg's uncertainty relation. But here it is the one for momentum and position. And the thing is, again, if one looks at electrons in normal metals, for example, and looks at the relation for energy and time, one finds that the relation is fulfilled at temperature exactly where also superconductivity is found, which is roughly in the range of some 10 Kelvin above absolute zero temperature. Yeah, that's the thing, basically, I found, that Heisenberg's uncertainty relation for energy and time is fulfilled at superconductivity temperatures. Yeah. If it is inserted into the Joule formula, the fundamental microscopic formula for the electrical resistivity, which can be done if at the electrical resistivity and superconductivity is looked at from a new perspective. But okay, that's another story and topic, this new perspective. And what I wanted to say now, say to you, the young generation of physicists, is again basically that this new idea could again be something, after quite some time, yeah, something big in physics. But of course only could be. To say more, it is too early now, or of course to promise more. But, and of course in the end, it is up to you, everybody yourself, to decide in which direction of physics you would like to go. Where, into which you would like to put your physics time and energy into. So in this sense, this is just another option. Another option you can choose from, in which I wanted to present. And that's what I've now also done here. And I can say now goodbye to you, dear viewers, young and old. Goodbye.